Okay, the Coulomb's law. Now, what does this law deal with, and what is this law all about? Now, this law is basically the law that gives the force of interaction between 2-point charges. We know that point charges, they can attract or repel each other, yes or no, depending on their sign. For example, if you have two positive charge, then in that case these two positive charges will repel each other, or maybe two negative charge, they will repel each other. Repel means that they will move away. They will exert a force on each other and they will move away from one another. But if the charges are opposite in nature, then they will attract each other, means they will go and meet one another. All right, so basically we understand that between 2-point charges there is always a force of interaction between them. Got it? So we don't know the nature of this force. All right, so in order to know the nature of this force and how the interaction process comes into play, we look into Coulomb's law. Okay, so let us see first what is the statement of Coulomb's law. The electrostatic force of attraction or repulsion between two static point charges. What do you mean by static? Static means the point charges are not moving, they are stationary. Two stationary point charges is directly proportional to the product of their magnitudes. Product of their magnitudes. What magnitude? Means the product of the charge, and inversely proportional to the square of the distance between them, and acts along the line joining the centers. Okay, so let's say we have 2-point charges. Let's say we have this charge out here and another charge and another charge right there, let's say. Okay, and this is the line. I'm just drawing a line. All right, I'm just drawing a line. Actually, there is no line that joins them, so I'm just drawing a line just to indicate that there is some distance between the two charges. Okay, now let's say this charge is Q1, okay, the amount of charge there, and this one is Q2. Both of them are point charges, so there will be a force of interaction between these two charges. All right, and let's say the distance between the two charges is R. Okay, so the force of interaction, let's say they are both positive charges. So if they are both positive charges, they will repel each other, right? So there will be a force of interaction opposite in direction. Okay, so let's say a force F out here, right? So according to this law says that this force is directly proportional to the product of the charges. That means directly proportional to Q1, Q2. That's the first part. The second part, it also says that and inversely proportional to the square of the distance between them, and this force F is proportional to 1 by R square. So therefore, if we combine these two, we get F to be proportional to Q1, Q2 by R square, or F is equal to K Q1, Q2 by R square. What is K here? K is a constant of proportionality. Okay, or you have F is equal to 1 by 4 pi epsilon naught Q1, Q2 by R square. Let me put this inside of a box. Okay, where K is equal to 1 by 4 pi epsilon naught, and this is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. All right, and this is called epsilon, EPSILON, epsilon naught. Okay, this is equal to 8.855 4 into 10 to the power minus 12. The unit of epsilon will be just the opposite to the unit of k, because k is up and epsilon here is down. So it will be Coulomb square per meter square per Newton. Got it? Is the, this has a name, permittivity of free space. Okay, so that is basically the name of epsilon. It is what? The permittivity of free space. Got it? Okay. Now this is, let's call this some equation 1. Equation 1. Okay, so equation 1 is Coulomb's law. Coulomb's law in free space. In free space or in vacuum, or in air. Okay, so if you want to write the, if you are asked to write the Coulomb's law in free space or in air or in vacuum, then this is the expression. Now in any other medium, how do we write the law? The law is written as F is equal to 1 by 4 pi epsilon naught epsilon r q1 q2 by r square. What is epsilon r, by the way, here? Where epsilon r, this is the relative permittivity of the medium. Understand? Sometimes instead of epsilon r, we write here k. We write k. Okay. This is also equal to capital K, not this small k, this is small k. Alright, and this one is capital K. Got it? And what is capital K? Capital K here is the dielectric constant of the medium. Okay, you will learn about the dielectric constant when we do chapter 2. Okay, so this is the Coulomb's law in scalar form. Why? Because it gives only the magnitude of the law. Okay, so you can see here that there is no unit vector, there is no sense of direction. Okay, it doesn't tell anything about the direction of the forces, right? It only gives the magnitude. Got it? So let us do now the Coulomb's law in vector form. All right, so again here let us consider two charges. Let's say we have 2 point charges, this one and this one. Okay, let me color this, put some color here to make it look more nice. All right, and then we draw a line. Let's draw with red. Okay, from this point to that point. Okay, this is a dotted line. Basically the two charges are not connected. Okay, they're just there in space. All right, and this line is just an imaginary line. So let's say this is q1 and this is q2. Understand? So there will be a force of interaction. Okay, so let's consider these to be both positive charges. Right, so there will be a force. Let me draw with blue. Okay, going from here in that direction. No, in this direction, and another force from there in that direction. Okay, so let's say this is F12 and this is F21. What is F12? force on Q1 due to Q2, and this is the force on Q2 due to Q1. Okay, now since it is the vector form, let us consider a unit vector. Okay, we're going to draw a unit vector. So a unit vector in that direction is R12, and a unit vector in that direction is R21. Okay, so this is a unit vector pointing from Q1 to Q2. This is the unit vector pointing from Q2 to Q1. Okay, and the distance between them is R. Let's say distance between the two charges. Okay, so that means from that point to that point is R. Okay, so by Coulomb's law, you have F12, this is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, but now I've written this force in vector form. So this is the magnitude part. Okay, so this part is the magnitude part. Therefore there should be a direction also, and that direction is represented by the unit vector. Now which unit vector we are going to put? Okay, this one or that one. So this force, if you look at this force, it is going in that direction. That means it is going from Q2 to Q1. So the unit vector also, we should put that unit vector which is in the same direction. So this one. So we will put a unit vector here, R21 cap. Alright, so that's equation 1. Similarly, F21 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Now which unit vector are we going to put? Look at this force F21, this one pointing that way. So this is the unit vector that we need to put. Okay, R12 cap. Understand? So basically equation 1 and equation 2 is the Coulomb's law in vector form. Alright, so some important points that we can discuss out here. Okay, now we know that R12 cap is equal to minus of R21 cap. Yes or no? We know this very well. What does this mean? It means that the unit vectors are equal in magnitude, opposite in direction. Okay, because there's a minus sign out there. So therefore, what is let me see. Therefore, F21. Okay, let's take F21. Therefore, F21 bar, this is 1 by 4 pi epsilon naught Q1 Q2 by R square. Instead of R12 cap, we can put minus R21. Yes or no? We can put here minus R21. Okay, so this minus sign can be taken to the front. So you have 1 by 4 pi epsilon naught Q1 Q2 by R square R21 cap. Now what is this part equal to without the minus sign? That is equal to F12. So therefore you have F21 is equal to minus of F12. Okay, so that means the two forces are equal and opposite in direction. Equal in magnitude, opposite in direction. Or so let us take magnitude. Magnitude means if we take the modulus F12 modulus, this will be equal to F21 modulus is equal to F12 modulus. So what does this mean? It means that the two forces are equal in magnitude. So it means that the force with which this body, this charge, is pushing that is the same as the force with which this charge is pushing that. Okay, and they are equal, they are opposite in direction. Not only that, let me write down those important points out here. So first point here is equal in magnitude, and opposite in direction. And number two, the two forces act along the line joining their centers. Okay, THEIR, their centers. So because of that, the electrostatic forces are central forces. Okay, you will learn more about central forces later. Understand? So from the vector form, we have these important conclusions. So first of all, the forces are equal in magnitude and opposite in direction. Not only that, they act along the line joining the centers, as can be seen in this diagram. So the two forces, this is the line, the red line, that's the line that joined the center of one charge to the other charge. So those forces are acting exactly along those centers and along that line. That means that if you apply force to a charge, the point of action of the force would always be the center of the charge. Is it clear? So this is the Coulomb's law in vector form and in scalar form. The principle of superposition. Now, what does this principle talks about? You remember the Coulomb's law. The Coulomb's law is a law that gives the force of interaction between 2-point charges. Alright, so it is a 2-point charge system or a two-body interaction. Okay, now in most cases there are not only two charges in space. There can be a number of charges in space. Alright, so how do we find the total force on a single point charge due to all the charges present in space? So to do that, we have to apply the principle of superposition. Now, according to this principle, it says that the force on any charge due to a number of charges is the vector sum of the forces on that charge due to all the other charges. The individual forces are unaffected by the presence of other charges. Now let us suppose, say, we have a number of charges in space. Let's say we have this charge Q1, or this charge, let's say we have here Q2, we have here Q3, and let's say Q4. Okay, so we want to find the force that this Q1 will experience due to all the three charges. So it is very clear from here that this Q2 will exert some force on Q1. Similarly, Q3 also will exert some force on Q1. Similarly, Q4. Now, the kind of force that they exert would depend on their signs. Okay, so let's say this is Q1 here is a positive charge. Let's say Q4 is a negative charge. Q2 here is a positive charge, and also let's say Q3 to be a positive charge. Got it? So what will happen here between Q1 and Q2, since they are both positive charge, so this Q2 will push Q1, right? It will push means it will exert a force in that direction. Okay, so in which direction will it exert a force? Let me draw using this color here. So it will exert a force in that direction. Okay, so this is the force F12. All right, F12. What is this? What is F12? F12 is the force on Q1 due to Q2. What about Q3? Q3 is positive, so Q3 also will exert a force in which direction? In this direction. Okay, it will push. So this will be F13. All right. Okay, what is F13? F13 is the force on Q1 due to Q3. What about Q4? Q4 here, it is attracting. Yes or no? Because this is minus, so it will attract towards itself. So it will exert a force in that direction. Okay, so I want to draw this a little more, so it will exert in that direction, little further like this. Okay, so this is a force F14. Do you see? So, oh sorry, what am I doing? Made a big mistake out there. Yeah, enough. F14. All right, so you can see here that there are the three forces acting on Q1. Now, how do we get the resultant force on Q1? We have to use the vector sum. Okay, right. So basically, it says that suppose if the system is like this, then the total force on Q1 is what is F1. This will be the sum of all the three forces. So that will be F13 plus F12 plus, let me write F12 first. Looks funny to write F13 just to maintain the uniformity. So this will be F12 plus F13 plus F14. Got it? And what is F12? That will be 1 by 4 pi epsilon naught. So 1 by 4 pi epsilon naught will be common out here. So I can take that as common. 1 by 4 pi epsilon naught. Then here, inside of the bracket, it is the interaction between this force, this charge and that charge. So this will be Q1, Q2 by R12 square. Plus the second one is between Q1 and Q3. So you have Q1, Q3 by R13 square plus Q1, Q4 by R14 square. Okay, so this is a system consisting of only 4 charges. There can be many more charges. So it continues if there are n number of charges. Okay, so this is nothing but the principle of superposition. The equilibrium of charge system is an important topic in this chapter, especially while doing problems. Okay, so I want you to understand this nicely. All right, so what do we mean by equilibrium? First of all, what do we mean by that? When we say equilibrium, what does it mean? So basically, when we have, let's say, 2 charges in space, okay, let's say we have a point charge here. Let's say we have a point charge Q1, and this is a positive point charge. Another point charge here Q2. Say both of them are positive point charge. Now, what will happen to this system of point charges? Will they remain in their respective positions? See, I'm just bringing from somewhere, I'm putting Q1 here, and I'm bringing from somewhere and putting Q2 there. So what will happen here? We know from Coulomb's law that they will repel each other, is it not? They will repel each other, so that this will experience a force in that direction, and this one will experience a force in that direction. Okay, and the two forces are equal. So because a force is acting on this, therefore it will move in the direction of the force. Similarly, this one, it will move in the direction of the force. So this system what will happen to these two charges? They will drift away. Okay, they will move apart from each other. Got it? So such a system is an unstable system. In other words, we say that the two charges are not in equilibrium. Suppose if I have Q1, which is a positive charge, and Q2, which is a negative charge, what will happen? They will attract each other. Yes or no? So attract each other means Q1 will move that way and Q2 will move in that direction. So these two charges will move nearer and nearer and they will approach each other. So again, this is an unstable or an unequilibrium system. Understand? So how do we make the system equilibrium? Equilibrium means if I'm able to put these charges and make them stationary, if I'm able to fix them in their respective places. So how do I do that? Okay, how do I do that? So what I can do out here is I can use a third charge. Alright, I can use a third charge, and using the third charge, I have to place the third charge somewhere so that now the system will be in equilibrium. Understand? So let us consider, first of all, a system containing of two charge, and both of them are positive, or maybe both of them are negative. Okay, let's say I have a charge out here. Let's say this charge here, Q1, both positive, and another charge here, Q2. Got it? And what is the distance between them? Okay, let me just draw a line just to show that they are at some distance from one another. This line is actually not a rope or a thread that joins the two charges. Okay, so what will happen here? Obviously these two charges will be going away from each other, isn't it? This one will go this way and this one will go that way, and they will move farther and farther apart from each other. I think that is clear, right? Because they suffer force of repulsion. So what I do, if you have a charge system where both the charges are same sign, then you have to take a third charge and put it somewhere in between them. Okay, somewhere in between them. That means along the line joining them somewhere. Alright, so let's say I put a third charge somewhere here, and that third charge is Q. Understand? Okay, let me use red color. Alright, red is more visible. Okay, now, and this third charge, it must be of what sign? Can you guess what sign, whether it is a positive charge or a negative charge? Okay, so here this one is trying to go that way, so so using this charge I'm trying to pull it that way, so this must be a negative charge. Okay, right, so what will be the forces acting on this charge? Okay, that is what we are interested. Obviously this charge will experience the force due to this and also due to this, right? So first of all, this charge will pull this. Okay, it will pull this in that direction. Okay, so from here it will pull in that direction, okay, with a force F1, let's say. Similarly, this charge will pull this in that direction, so it is acting from this point, but at this point the force is coming from here in this direction. Okay, so we call this force F2. Got it? So since the two forces are vectors, and from a theory of vectors, I don't know whether you remember or not, in class 11 we have learned that if you have two vectors acting in opposite directions, let's say we have a vector A bar and a vector B bar, both of them are acting at this point O, and they are making an angle 180 degree with each other. They are acting in opposite direction. If suppose A bar, magnitude of A bar is equal to the magnitude of B bar, then what will happen? We say that the two vectors, they balance each other, right? So this point O will not move. Understand? So we want this charge to not move, so that can be done, or that can happen only if what? If the magnitude of F1 is equal to the magnitude of F2. Understood? So suppose if the question comes in the exam, you have a charge system plus Q and plus Q1 and plus Q2. Where would you put a third charge so that the system will be in equilibrium? So you say in between. So let's say you put the third charge at a distance x from Q1. Okay, so you have to find the value of x. So what do? You use this concept. Use this. Just find the expression of F1, find the expression of F2, equate them, then from there you can find x. All right. So also if the two charges are of the same sign, or are of negative sign, say this is minus and this is also minus. So the same thing here, the same concept applies. Okay. Where do you put the third charge? Again, somewhere here in the line joining them. All right, so that will be the third charge. Got it? So again here also there will be a force. This third charge will be what? It will be plus or minus. It will be plus or minus. So this third charge now should be positive. Okay, right. So again here there will be a force. Now this positive charge will pull this one, right? In which direction? In that direction. And it will pull this in that direction. Okay, so it will pull with the force F1 in that direction, and it will pull Q2 with a force F2 in that direction. Understand? So again here they will be in equilibrium only if the magnitude of F1 is equal to the magnitude of F2. Understand? Make sure that it is magnitude. Got it? So that is one point. Now what will happen if suppose both the charges are not of the same sign? What will happen? Now how will they be in equilibrium? That is basically the question. B. If one is positive, the other negative. Okay, so let's say I have a charge out here. So this is plus Q1, and another charge out here. This is minus Q2. Understand? And this is the line joining their centers. Okay, all right. Then now the question is, where will you put a third charge? Now if you have these two charges like this, then they will approach each other because they are experiencing the force of attraction. Yes or no? How do you make them fix in their position? So you have to put the third charge either here or here. Okay, either on the left side or on the right side, but not in between. Remember that. If they are of the same sign, not in between. If they are opposite sign, not in between. If they are of the same sign, then you have to put in between. Understand? So let's say I put this third charge here, somewhere at this point. Let me undo this. Again I'm drawing this line. Somewhere you have to put here. That is the way, that is the position of the third charge Q. Is that clear? Alright, so what will be the force acting on this third charge? Okay, so this third charge, it can be positive or negative. Let us choose positive. Alright, so if it is positive, then it will push this one, is it not? It will push this, so that means it will exert a force in that direction, in this direction. Okay, so this force here will be F1, and it will pull this one. That means from here it will pull this one, it will pull in that direction. Okay, it will pull towards itself. That means at this point, where is the direction of the force? In that direction. All right, so this is F2. What is F1 and F2? F1 is the force that this charge repel Q1. F2 is the force that this charge attract Q2. So again here, when will the system be in equilibrium? Only if F1 magnitude is equal to F2 magnitude. Is that clear? So basically the technique is the same. This is the technique or the idea that you have to use. Only thing is the positions. Where do you put? Okay, so that is important. Got it. Alright, so let's now discuss a charge which is hanging from some rigid point. Okay, so let's say we have two metallic spheres which are very small, and they are hung from this point P. Okay, they are hung from a rigid support. So you can see here that the two spheres or two metallic balls, they are touching each other. So what will happen if I give a charge Q? If I give a charge Q to one of the balls, and because they are metallic, what will happen? The charge will flow to the other ball also, so that both the balls will have an amount of charge Q by 2, Q by 2. Is it clear? Equal amount of charge. Understand? So this is due to the process of conduction. Alright, so now what will be the nature of the charge present? So I'm giving positive charge, so obviously the charge present in the first ball will be a positive charge. Similarly, the second ball will have a positive charge. So because they are positive charge, what do you think will happen now? They will repel each other, is it not? They cannot come in contact anymore, because now there will be a force of repulsion. So how will the diagram look like? Okay, so you see here that the two balls, they will start to repel each other. Now, why do they repel each other? The reason is because there is a force of repulsion which are in opposite directions. Let me draw this nicely. So there is one force in this direction and another force in that direction. Okay. And the magnitude of these two forces are, let's say, F. Alright, okay. Now what are the forces that would act on this body? Let us consider this body. Okay, so here there will be the weight of the ball which is acting vertically downward always, right? The weight is always acting vertically downward. That is the property. Okay, so what is the weight here? mg, where small m is the mass of the ball. And also there is another force along the string which is called the tension. Understand? So they will come like this. They will be far from each other and making an angle theta with the vertical. Okay, so how do we get an equilibrium? Okay, how do we solve this equation? I mean this problem. So this is obviously equilibrium now. Alright, so how do we do this? The easiest method is for us to resolve the tension. So resolve the tension means we resolve it into its rectangular components, okay, into its sine component and the cos component. So resolving the tension, we get one component in that direction and another component in that direction. So this component is making an angle theta. I think this is very clear because this line and this line are parallel, so this angle and that angle are alternate angles. And this component here is t cos theta. Another component in this direction is the t sine theta. Got it? And since this is now in equilibrium, it means that the opposite forces will balance each other. So that is t sine theta. T sine theta, this will be equal to the opposite force F. Okay, that is equation 1. And t cos theta, this will be equal to this opposite force mg. That is equation 2. So solving 1 and 2, using 1 and 2 we can solve many things. For example, we can find the angle that this string makes with the vertical, or maybe we can find the value of F, or maybe we can find the tension out here. Alright, so these are the equilibrium system that I want to discuss with you, and these are important for the numerical exercises. Thank you.